So, talking about the match that was just was it 2 weeks ago or so, and there was the Nature article that appeared in January. So it tells quite a lot about how AlphaGo works, but I'm sure the team must have been working on it after. So it describes AlphaGo what it was last October. So we might not be sure what is hidden in all the secrets. And some people say it was a huge surprise that the computer won already. But I looked back to my AI course slides from spring last year and predicting that actually there was a new approach to computer Go just last year that was very different from the current state of the art and reached almost the same performance. So by putting those two things together, it was many people actually predicted that okay, if we put them together nicely, it will be really strong, and that's what they also figured out at DeepMind. So there we go. We have the Nature article and the big win for the AI. So in some sense, we are still not very far. So if we compare, like Lee Sedol was using just one brain, and the brain uses something like 20 or 30 watts, and the whole body is something like 80 watts, whereas AlphaGo spent quite a lot of computing power, more than 1,000 CPUs and 176 GPUs, and that's on the order of at least 100,000 watts. I don't know the exact numbers.
Was this during training or evaluation?
During evaluation. Yeah. So my talk, I will describe the game of Go. Hopefully a fresh view because many probably know it already, and then the two approaches and how to put them together. So, firstly, about game of Go, it's the name Go is Japanese term that is used internationally, but in Korean it's Baduk and in Chinese Weiqi. It's a two-player, fully observable, deterministic zero-sum board game, just like chess in that sense, and it's the oldest game still played. It has simple rules. It's actually the most popular board game in the world. It's very popular in Asia, so that's why it might sound surprising because some people here have never heard about this game. So to describe the rules of the game, we can jump immediately to the point where Lee Sedol resigned the first game at this position. So the game proceeds that starting from the empty board, you add stones of your own color one by one to the empty points until the game is finished. And the player who controls a bigger area on the board wins. And Lee Sedol played black here, and to most of us people, this is not clear at all what is happening. Why should black resign? So what was Lee Sedol thinking? Something like this, that black is controlling the points marked with black and white is controlling the points marked with white. And there's some borderline things which are not clear yet, but he's so certain of his estimate that he's estimating that white is leading a bit, and that's why he resigned. Amateur players would have finished the game by making the last moves, and then the board would look something like this. Now the edges between the black and white areas are clearer, they are not open anymore, and you can count the exact score and see that white wins by 4.5 points. And if you're a really beginner, this is still not so clear because there are some white stones in the black area and vice versa. So you might play the game even further and fill out all the areas, and now it's really, really clear what is black's area or white's area. And actually this AlphaGo or the Monte Carlo tree search uses these rollouts that is sort of a very simple AI solution that is being used inside the bigger AI. You can think of it as a swarm intelligence, that you have a nest of ants, and the ants are really simple, but the nest is more intelligent. So those rollouts or ants would play the game until the very end, this far, and to make it obvious who is winning. Okay, so about the rules of Go, the winning is about who's controlling more area, and there's the capturing, that the group of stones is captured when it loses its last contact point to an empty point. So here the black stones form a group, and next to this black group there's only one point that is empty. That's called the liberty of the black group. And by taking the last liberty like this, the black stones will be removed from the board. And a bit more complicated example, we have now 4 black groups here and 4 white groups. So you use only the 4 main directions to see what is connected and what is not. And white can play here, even though white right now wouldn't have any liberties. So white can only play here because it'll capture the black stones. So I said, what is happening in the corner? Black stone only has 1 liberty left, so it's very easy to capture from the very corner. Yeah, so I said the rules of Go are simple. As a comparison, here are the rules of chess. They don't fit into 1 page, so I put them on 2 pages, so have a quick look. And compared to that, the rules of Go are pretty simple. These are all the rules you need, all the exceptions, and funny stuff is here. So I'm not going through that, but I can provide you the slides afterwards, so you can get to know the game. So, okay. So what follows from the rules? It's first of all easier to make territory in the corner. So Go is all about using your stones efficiently. So to surround 9 points of territory, so this 3x3 blocks, you'll only need 6 stones if you do it in the corner, but 12 stones if you do it in the middle of the board. So that's why in the opening of the game, you tend to play near the corners. And this is the opening of the first game. So Lee Sedol is black and AlphaGo is white, the first time they meet. And the first moves are all near the corner. And if you count, it's either the 3rd or the 4th line from each side. And even the next moves are all 3rd or 4th row from the sides up to this point. So this is how openings often look like in Go. So why is Go played on 19 by 19 grid? And one reason why it's exactly this size is that I mentioned this 3rd and 4th line, that they are about equally important. So we get lots of different openings. You can play lots of different styles by choosing more the 3rd line, which emphasizes the immediate territory, or the 4th line, which emphasizes future fights on the board. And in this case, the the area on the edge of the board is slightly bigger than the middle one, even though it might look like the middle is bigger, but it's not. So they are about equally important. And why is it a square grid? If you would play Go on some other type of board like triangles, if white is now blocking black stones by playing here, white is always connected, so white forms a single group here. But if you play on the square grid, if white blocks the black stones, black can still cut. It's called a cut, and splitting white into two separate groups, and then those groups might have to fight. Maybe one of the groups might get captured, and this fighting is the spice of this game, and that's why this square grid makes it interesting. Yeah, so Go should be in the easy category of AI problems. If this is the typical categorization of AI problems, so it's in the same category as chess. So it's fully observable, no secrets, no hidden cards or something. You have two players. That's almost the only complication. It's deterministic, no dice or anything. It's sequential. You have multiple moves to decide before finishing the game. That's a complication. It's static. So while you think, the world doesn't change. Like if you would play football, something would happen if you stop and think too long. It's discrete, and you know all the rules in advance. But still, Go has been a very tough thing for AI. So these are sort of a historical even matches between AI and the best players. So 1998 in chess, AI was already stronger than the best human player, and but the best Go AI was still very weak compared to best humans. The best humans could give some ridiculous handicap of 29 moves and still win. And there was some nice progress. In 2006, Monte Carlo research-based AIs became better than the traditional approaches, and soon a computer could play the best humans with a 9-stone handicap, which is already reasonable. And this year, the computer wins. So it has been a very, very hard problem, and maybe one reason is that when people are playing Go, they have to use both their intuition, that something just feels right or looks right, in addition to sort of pure logical calculations. Sometimes you have to think forward and just like in chess, consider what happens with this sequence of moves and so on. And this kind of combining the two parts was tough for computers. And this approach that AlphaGo has this exactly these two ideas that somehow support each other. Okay, I talked about some of these things already. So why Go was difficult for AI? Well, maybe a better question would be why is Go easy for people? Because it's the comparison against people what makes it hard for the AI. So it's very visual. If you just add things one by one, it's very easy to see in the mind's eye what happens after 8 moves. For instance, if I have an image like this, it shows a typical sequence that might happen in the corner of a Go game. if you make some similar image for a game of chess where you visualize 8 consecutive moves, it would be really difficult. But this is very clear, at least for any Go player. Branching factor is large, so it's 361 points on the empty board. So no brute force solution can be used. And actually, Antti Tarvainen here made a small calculation that if you make a brute force search with 1 billion nodes in game of chess, you could get as far as 15% of the typical game length with this kind of a search. But in Go, we would only get 2% of the typical game length. So it doesn't really work, even with a billion moves evaluated. And heuristic evaluation is difficult. In chess, it's good enough to just count the pieces, and whoever has more pieces is winning. In Go, it doesn't work like that at all. And also, the horizon effect is very strong. Like if you think, let's say, look 10 moves into the future, in Go, it's very often the case that it's very easy to delay some capture by, say, 20 moves, even though it's for a human player, it's really obvious from the beginning that those will be captured in the end. It's just delaying the capture by adding more stones to the group. So having a fixed length of horizon, which is often the case in chess AI, that you look exactly 10 moves ahead, doesn't really work. Okay, so now to the actual AlphaGo. What does it contain? So the first part is the deep learning part that I will describe. And actually, AlphaGo uses 4 different networks. And I'll go through all of them. So 3 of the networks will predict the next move, and I'll call it A for action, given the state. So S is for state, or the whatever the board contains now. So the 3 first ones will produce as output the probability distribution over the next move. And the 2 first ones are based on human expert positions, and the 2 last ones are based on self-play positions. And the last one evaluates the value of a position. So basically, who's winning, or what's the probability for the black player to win, for instance. Okay, so the supervised learning part, or using the human expert moves, that's done in networks 1 and 2. So the task is to predict the next move that the human would play. And they used 160,000 game records from 6 to 9 dan amateur players. So there are not enough game records from professional players that they could use. It's more important to have a larger data set. So they used amateur players records, but very strong amateurs. And basically the learning algorithm is really simple. It's just gradient-based learning. So you try to maximize the log probability of the action given state. And you know the right answer in your data set. So it's supervised learning. And so they had 2 networks. One is a very small one called rollout policy. It uses just handcrafted features and no hidden units. And it's very fast, so just 2 microseconds to evaluate this network. And it will be used in those rollouts, this AND thing that I mentioned. And then another one is called the Supervised Learning Policy Network, and it uses a convolutional network. I'll have the next slide about it. And it takes 4.8 milliseconds to evaluate, so it's pretty slow already. But it can predict pretty nicely the human moves. It has a 57% prediction accuracy. So in the majority of cases, it can correctly guess the next move that the human player would do. So it can be used to narrow down the search quite a lot. And these ideas are not very new. So first time convolutional network was used for Go in 2008, but there was quite a lot of development in deep learning, so the idea was revisited last year, and the results were surprisingly good. So this is what sparked the AlphaGo project. And some of the authors of this Madison, or maybe all of the authors from this Madison paper are actually in AlphaGo team. Yeah, so convolutional network. For those of you who know convolutional networks already, here are the specs of how the network worked. So basically it has it tries to output the probability of the next move in each location. So that's visualized here, that this might be the most probable move here. And it has, this network has 13 layers, and each layer has the same size, 19 by 19, as the board. They don't use just the raw board signal here as the input, but they use some handcrafted features to make it 19 by 19 by 48 instead of 19 by 19 by 2. 2 would be just the white and black stones in 2 channels. That would be the raw board state, but they use some other features. And yeah, it has about 20,000 parameters, so the weights in the neural network that are randomly initialized and then learned using this gradient-based learning. And to give you an idea what is a convolutional network, or what is a convolution, what do each of these layers do? It performs a convolution operation. So just giving an example, if you take this input, which is an image in this case, and you convolve it with these filters, you get an edge detector. The first one finds horizontal edges in the image, and the next one finds vertical edges in the image. And these convolutional networks are what is used in computer vision these days. So it's an interesting idea that somehow a Go player can just have a glimpse of the board and know what is a good move already. So it's sort of using the vision or in some sense intuition that this convolutional network is mimicking the same thing. Okay, now we have the two networks covered on the left, and then we go onward for the third network, the reinforcement learning policy network. And it uses the same architecture as the second network. So it's this slide applies to both the second and the third network. And it's initialized by the end result of this supervised learning, the second network. But then it's further trained by self-play. So it started to play games against a copy of itself. and lots of games, at least 30 million games. And if a human, let's say a human might be able to play 10 games per day if he or she plays really fast and uses all the time for just playing. So to get into 30 million games, you would have to do this every day for more than 8,000 years. So let's say that AlphaGo is really experienced in playing Go. And from self-play, the algorithm that further trains the network is basically that you play a game, and if blacks happen to win this game, you sort of increase the probability of those black moves that happen to be used, and you decrease the probability of the white moves that were happened, because there's some randomness in this self-play. It's based on this policy network that outputs the probabilities of the next move. So if the moves are chosen according to this probability, there's some randomness, and that's how it works. And the policy gradient, I didn't have the derivation here, but it's derived from a completely different starting point than the supervised learning. But actually the resulting learning rule looks very, very similar to the supervised learning rule. There's only this thing here extra, which is the Z telling it's the outcome of the game. So it's +1 for the winning side and -1 for the losing side. So the update algorithm is exactly the same but you only trust the moves of the side that happen to win this game. And you sort of learn away from the moves that happened to used by the losing player. And yeah, so this actually reaches a very strong Go player already. It's a 3-dan amateur strength. Let's have by the way, at this point, a bit of voting by hands at who knew the game of Go before coming here. So this, okay, majority, and who has a rank? Okay, and who has a Dan rank? 2. And who is stronger than 3 Dan? No one. Okay, so at this point they reached the performance of that would beat everyone in this room. And it doesn't have any look ahead, just has a glimpse of the board and chooses a move. So it takes 4.8 milliseconds per move, and it uses a single GPU for that. So it doesn't need this huge computer that they used. So it's a pretty, actually surprises me that this is so strong and so fast, that why did they use to have this huge computer and making the final steps for the professional strength. You really needed much more computational power. So maybe if someone further continues the Go AI projects, they might get it just as a single computer wins everyone pretty soon. But of course now it's not so interesting, because this was the big event and that had millions of people watching, but that's done. So let's see what happens. And then the final 4th network that tries to output the expected outcome of the game. So I have this Z variable here, -1, +1 for winning or losing. So the expectation of this Z, assuming that the game is played using the reinforcement learning policy, so the policy from the previous network. So that's then the outcome of the game will be a random variable, and you try to predict the expectation of that variable. And the architecture is a similar convolutional network, except for the very top part where you have a fully connected layer and a single output. So now instead of trying to output something for every point on the board separately, you output just one number, which is the expected outcome. And this is actually just a regression problem. So you use a data set of at least 30 million positions, and to prevent overfitting, you take those positions each from a different game, such that because there's sort of a loophole that if you just memorize the games, you recognize, okay, this is from this game, and I know the outcome of this game. It might overfit by just memorizing the positions, but if each position is from a different game, it cannot do that. So it's a regression problem. You try to match the expected outcome V to the sampled outcome Z. So, in a way, simple. And now we have all the 4 networks trained. And what do we do with them? You remember the third one was the really strong and fast algorithm, and you toss it away. That's somehow disappointing for me, at least. So you use the rollout policy, the very fast policy for evaluating nodes. You use the supervised learning policy network to guide search, and you use this value network to also evaluate nodes in the search tree. So we get to the search tree part, putting it all together. That's a very tough question. I do have some idea, but yeah. So the goal of the policy network is to make as strong moves as possible, but it's a different goal from guiding the search. Like the question that you want to ask is this move worth thinking about? And it's a very different question from is this move worth playing? So you play the move that you know that works, but you might have to think about moves that might work or don't work, but you will find out if you think about it. So it's actually there's very little interplay between the search part and those networks that this traditional search algorithm just uses the deep learning things, and the deep learning thing is not used to guide the search properly. So there could be better interplay between the search and these networks. So it might be possible to come up with a training criterion that is especially useful to guide the search rather than to find the strongest moves. Okay, so Monte Carlo tree search. So the idea is that you have your current state and you do self-play from that state onward. So you do simulations of the game from that state onward. And AlphaGo does about 17,000 simulations per second. So you'll get a big tree with that. So each simulation or each path adds a new leaf node to the search tree. And it's not a full width search as you have in chess, but it's sort of concentrating on the best moves, making it very deep for the best moves and less deep for the other moves. And after you've spent some time doing this search, the final choice for the move is the node that was chosen the most times. So I'll go through an example. And it doesn't really matter whether it's a single agent, multi-agent, adversarial, or whatever. So this algorithm works for all kinds of tasks. So now I'm making a tree here. So the root node on the top is the current state of the game, and its children are the next moves. And I'm showing the number of wins and number of trials for each node. So you might first try this path, and then you simulate the game using the rollout policy until the very end. And okay, if you happen to win it, good, you mark it as a win. Next time you might lose, and with the third option you might win. So now, as I said, each simulation adds one more node to the tree, and you always update all the counts along the path in the tree. So here we start to notice that, okay, maybe this move on the left is a good one, because it gives more wins than the other ones. So to give the details from AlphaGo, you have how to choose the node while you are within the tree. You use this it basically chooses the node that is currently considered best, and this queue is stored for each node, and it has the evaluation of that node. So you choose the best one, but there's also a bonus, and this bonus here is 5 times the, well, 5 is just a hyperparameter they used 5, and this is the supervised learning policy network's probability for choosing that move. So the more likely it thinks that a human would make that move, it gives a bigger bonus for that. So this is the part where it's guiding the search. But this bonus is divided by the count of how many times this action has been already tried. So it uses this bonus just as a sort of a prior. When it doesn't have the real information available, it just uses this bonus to guide the search, to first consider the best moves. And you always add one more node to the search tree, and it should be mentioned that this supervised learning policy network is only need to do it once for each node, and you run it whenever you add the node. So those two networks, the policy network and the value network, are the bottleneck of this algorithm. They are the slow things. So it's important to know that for each simulation you have to do just once the policy network and once the value network. So here at the evaluation of the new node, you run the value network, and you also make a rollout. So you play the game from that node all the way to the end of the game using the very fast rollout policy network. And then combining these very different two evaluations together, you also update the evaluations queue all the way to the top, sort of going back the same route that you came from. And those queues are updated to track the mean of the queues in the subtree below. And you have the two different types of evaluations that are combined all the time. And that's it. That's how it works. And yeah, as you all know, the AlphaGo won Lee Sedol 4 games out of 5. And here are some strength measurements from the Nature paper. So this is the October version of AlphaGo when it was still weaker. And maybe the interesting part here is the middle one, that if you disable some parts of AlphaGo, how strong is it still? So you can disable any one of the 3 parts, and it's still stronger than any other Go AI out there. And you can disable any 2 of those 3 parts, and it's still amateur Dan level. But only when they are all 3 are used together, then it's the strongest by far. And the strength that you get from going from a single machine to a distributed version is maybe relatively little, but that was still needed to win Lee Sedol. So on a single machine, it's a professional level already, maybe not the top professional. And I want to show you two interesting moves from the games. So there was a move by AlphaGo in game 2. AlphaGo was playing black and made this kind of a move. And it's called the shoulder hit because it's somehow it's to the connection of this diagonal move from the opposing color. And it's a very common move against a stone on the 3rd line. But in this case, it was already on the 4th line, so that then the shoulder hit is on the 5th line, and this is really unexpected. So Lee Sedol he had to leave the room, and it took him 15 minutes to come up with the next response to this. And they had both players had 2 hours in their clock. So spending 15 minutes on one move is quite a lot. And there were commentators which were like really top professionals, and one of them said that this was a mistake by Black, and the other one said that something like super surprising and very weird move. But it turns out that it was a great move. Maybe it's, yeah. I don't try to explain why I'm not such a strong Go player myself. So maybe the professionals will start using this new move in their own games as well. And it was a good move, and AlphaGo won this game, so it worked. But yeah, Lee Sedol also had his great moment. In game 4, there was this kind of a situation where Black has a really strong area, and all those white stones here are sort of hopeless. It looks pretty hopeless for White to try to do anything here, and this move here looks locally pretty bad. It doesn't stand out as being something that could work, and AlphaGo missed it and considered it very improbable move to come, and so White is sort of at the same time wishing to cut these two black stones and enter this area from the left, or maybe build a path to escape through this path, or maybe connect to these stones. So there are many things that might work out nicely for White, and if he gets one of them to work out, he'll win this game, and that's what happened. AlphaGo actually made some pretty weird moves after this one sort of went berserk. And totally missed this one. And something like 8 moves later, AlphaGo's own evaluation of who's winning this game dropped really dramatically, but not immediately, but after 8 more moves. So humanity still has hope. Compared to Deep Blue, so you probably remember Kasparov against Deep Blue in 1997. AlphaGo is different. It learns. Deep Blue didn't have any learning in it, and the hardware used in AlphaGo is about 100,000 times faster. That's simply because 19 years went by, and it still evaluates 1,000 times fewer positions per second than Deep Blue. So it's a really different approach that you really spend quite a lot of time on evaluating one position. So you can actually compute that you spent 100 million times more computations on a single position. And if you think about the applicability of this approach to other AI tasks, AlphaGo doesn't have anything that restricts it to, let's say, deterministic adversarial search. You can use the same algorithm in 1-player games or 3-player games or games with dice or whatever, or something else than games, for instance, like personal health, which medication should you try next or something. Whereas Deep Blue was clearly only for deterministic adversarial search, because it was based on alpha-beta pruning. Yeah. So if Deep Blue didn't really bring anything great into AI, there might be, well, it was so specific to chess or specific to 2-player games, but AlphaGo might be more applicable to other tasks too. Yeah, this was my last slide. I hope I didn't use too much of everyone's time here.
Oh, I don't have. Oh, now it's on. Thank you, Tapani. Now, time for questions. I'm sure we would all like to play the game of Go now. Do you have the board with you? Oh, okay, that was my question.
I don't know that. I think it wasn't discussed much on a Nature paper, and that's something they did mostly after the October version. So it hasn't been published how it is done. Oh, yeah, starting from scratch instead of using the human expert move. That's something they actually mentioned that they will be trying next. So what if they start this reinforcement learning from scratch? Can they still learn the game? And I guess this is much more difficult task, and it might be useful to start from smaller boards. So you first play 9 by 9, then move up to 13 by 13, and 19 by 19, and somehow try to generalize what you learn from the small boards to the big ones. Otherwise, I think it would take forever for it to notice anything reasonable. But who knows? Who knows? Yeah. Yeah. So when generating the search tree, it was mostly on the human experts. Yes. But the valuation, the value network was an important part, and that's what reinforcement learned. Yeah. Yeah, but they might be like this. The reinforcement learning policy network could still be used for guiding the search. It's not just not quite as good.
You can answer that question by showing a picture where you have lots of strengths. If you take the value network out, this one. If you take the value network out,
You,
it actually drops a lot on the strength. This split.
and the value network is based on reinforcement learning. Yeah.
I'm not kind of saying that. I'm just saying that this way to actually go to select the movie action is fundamentally important, right?
Yeah.
It's coming from the experience of the progression.
Yeah. Yeah. And actually, after the previous games, the October games, the people commented that AlphaGo seems to have a Japanese style, and and the games were collected from Keynote server, which is a Japanese server. So it still shows that like the human moves are still there pretty strongly in the AI. They didn't comment that after these March games, but I guess they still have a strong influence back there. So let's see. I'll be interested to this reinforcement learning from scratch. How would that look like, and would the style be completely different? Yeah.
Because in most domains where you're actually trying to use this kind of a system for health or robotics or whatever, then you don't have this human experts playing 160 times now. Or then you have just time to have 40 robots to that something.
Yeah.
But this graph doesn't show the strength of the machine if it has this Rollout value network and the reinforcement of all the network.
There's something like this policy network alone, which is here, and I assume that's the reinforcement learning. I don't actually know what does it mean. Which policy network is it?
Oh yeah, I don't remember.
But
What I was going to say is that it doesn't use any search like that.
yeah. So that's the.
That doesn't use any search. I guess all the other ones actually combine search.
Yeah. So this is the 4 Dan strength with 4.8 milliseconds of thinking, so more than amateur.
Yeah, but it's because network and rollouts are used for the same task, so they are like redundant. So they like I think that's why it's like it doesn't like dropping one of them doesn't drop the score as much as dropping policy network. That's why my guess why like dropping the policy network. So like the policy network is the most important.
Yeah. They will try, so we'll know. What's my guess? A little bit tough, but I think it'll happen. Yeah.
I can make a bet with you if you want. So my guess would be that it's going to work and it's going to produce similar results. I don't think it's going to be much different. It maybe I think it's going to be somewhat better, but it's not going to be like the game will look roughly the same as it will now.
So that's your prediction. It won't be like now it's the fourth and the fifth line that are important instead of the third and the fourth line.
We might.
But if they can start from small boards and then scale up little by little and try to.
There was a comment by DeepMind crew that they expected it to take additional 2 months of computational time to actually start from scratch compared to starting where they now did with the high-level language players.
Okay.
And I think in that case it will like the choice of the reinforcement learning algorithm is much more important because it will be important that they will efficiently like kind of backtrack the result of the end of the game to the very first moves so that they can learn the first moves.
Question on related to what happened with the game 4, the move 7 to 8. After that, AlphaGo actually started making moves that were clear errors for a human player and actually deteriorating performance quite a lot. And that it basically showed the symptoms that the old weaker Go machines had shown before. Do you think that kind of pattern that if somebody plays outside the kind of objective function, the algorithm, it deteriorates its performance? It's quite drastic if it happens for a real life application.
I think what. Yeah, I think what happened was that that when AlphaGo realized it was behind, and it tries to maximize its winning percentage, so it tries to make the rest of the game confusing. But the point is that it tries to make it confusing for itself, and it sort of then builds on its own weak points, like.
There was quite a few moves that were moves that even a kind of basic level amateur player would not make and were clearly kind of losing points for AlphaGo.
Do you have some comment on that? Or?
I think, well, in the game setting, AlphaGo doesn't communicate about its confidence of the move, but it's probably computing those. And so if you think of healthcare, for example, the
Yeah, and what I try to say about this confusing itself, like let's say there are 10 different forcing moves on the board, and you might play them in any order, and then there's the difficult part somewhere, some fight in the center, whatever. So because when in this game, this tree search, it doesn't generalize from one part of the tree to the other. So if it decides to first make 10 forcing moves in random order, and then try to solve the crucial part of the fight, the difficult fight in the center of the board, then it'll sort of create the 10 factorial copies of this difficult fight. So it's very confusing for itself. So by first playing these forcing moves, it's making things confusing for itself. And if it's losing, it tries to be confusing, but it's not not properly making the human opponent be confused, but itself it's confused. And
I want to. What about this situation? There's like one additional consideration is that there's kind of like a soft decision. Oh, decision boundary. No, I mean what's the word? I mean the like. Okay, in the search tree, first AlphaGo does the policy uses the policy network to choose the moves, and after that it just uses rollouts. And how it's like, what happens when it moves from the policy network part to the rollout part is that it starts to make more random moves. And so when it has like a difficult situation, I think there is a like tendency of it that it tries to move that difficult decision to the Monte Carlo part or the rollout part, where the result is smoother. It's not as black and white, but it has the kind of like it can count on the opponent of making random moves, which might be the better result for it than both of the players making the best moves. So that's might be another reason why it makes those like unnecessary moves.
One thing I noticed is quite interesting that if you maximize the reward function for the reinforcement learning and use that to select the next moves in the search tree, that's actually not the optimal policy as they say. What would be then the optimal policy, or the optimal criterion for the network for selecting the next moves in the search tree? Would it be some kind of exploration exploitation criteria, or what would be actually the optimum for that?
yeah, we could discuss that online. We had some ideas that we were bouncing with Antti, that sort of that if you estimate not only the winning percentage, but sort of the distribution over the distribution of winning. So then those, like that, if the network would also output its own estimate of its own uncertainty, then those moves that make the situation more uncertain are worth to check out more carefully. So concentrate some more effort in the tree search for them. So there are some ideas that could be done.
My initial estimate would be somehow
Yeah.
I have a question about this particular game situation. This move in L11 by Lee Sedol was called Hand of God, but what AlphaGo played afterwards, do you know if that was optimal? Because I think it played in K10 afterwards. I watched the game while it was going on, and I think that one of the commentators was saying that that looked like a mistake, that it should have played in L10 instead of K10. So I guess these games will be analyzed for years to come, but I mean,
Yeah, actually, yeah, Demis Hassabis tweeted about this move, that saying that the response to this Hand of God was a mistake, that the AlphaGo played the next move was wrong, that this was not actually winning yet.
so that's not a good move actually. It's a good move in the sense that it can be confusing, but it's not a good move in the sense that it would have.
Yeah, that there is a winning answer for this move. Yeah, it's not a good move in that sense. But maybe it was still the best move in some sense.
The only chance.
Only chance, yeah. Yeah, but they already did some analysis of it. That the next move was a mistake. I don't remember what was the
It was K10.
K10. It's too complicated for me. Yeah. Okay, are we done?
Okay, let's give a hand to our speaker again.